I think so. I hope so. Nice. So, thank you, Pietro, for the introduction. In the next 15 minutes, I will talk about lifted and long-range reasoning on graphs. These two topics are really connected to other topics that have already been explained in the past lectures and will be explored in the future ones. But I'll try to give an angle a bit different. And I hope you're fine with that, but in the next 15 minutes, we'll play a game, if you're fine with that. And the game is that we are going to ask a lot of informal and ill-posed questions. Okay? And we'll start the game by closing your eyes. Please, all of us, close your eyes. And we take an in breath and an out breath. And now I want you to forget that you are a computer scientist. And once you open your eyes, you'll become a chemist. Okay? Now open your eyes, and you are a chemist. So I want you to approach these 15 minutes with the eyes of a chemist. I'll give you a problem. The problem is you have this molecule, and I want you to reason as a chemist would, or you at least trying to, and try to see to approach the problem of whether this molecule is corrosive or not. I'll give you a few seconds to think about it.
What is corrosive?
That's a great question. It means that when you touch it, it hurts, or something like that. Can I say that? I said like a lot of informal and. Thank you. Okay. So the challenge here is just to think in a conscious way, from a different perspective of a computer scientist about this problem. And now I want you to raise your hand if, as a chemist, you are thinking in terms of message passing. Like if you're thinking like, I'm taking this note, I'm sharing messages. Are you doing that? If you're doing that, raise your hands. If you're not doing that, stand up. Great. Okay. Please.
Would you not say that physicists would think in terms of message passing and forces between the atoms?
I chose chemist.
So that's why you chose
That's why I chose chemist. Thank you for the question.
What about the orbitals? Because like I would think of this in terms of pushing kind of electron density to certain regions. Is that equivalent to message passing?
Yeah, more or less in the sense of what Petar probably was asking about. Yeah. Yeah. That's fair. And there is no wrong or right answer. It's just a feel. Like I just wanted to have a feeling about what you feel. Okay? As I said, a lot of informal questions, there's not a right. So when I started thinking about this in a conscious way, like a chemist, I'm not a chemist. This is the way I started approaching the problem. And so the idea is that like, in chemistry, we think about this problem in terms of functional groups often. Why not in terms of orbitals and stuff like that? Just because it's easier, like it's more intuitive to think about higher order structures like submolecules, which their own property that are already known. It's not intuitive, or it's not efficient to think in terms of orbitals and stuff like that to solve this kind of problem, at least from the perspective of a chemist. And if you think this way, there are some of these submodules that are already known to being corrosive. So in this case, like both these two functional groups are corrosive. And this is what we refer to as lifted inference or lifted reasoning. Like we try to raise our problem from its initial definition and define a new problem which is easier to solve. And the way we do that is to increase the abstraction level we reason about. This is somehow easy if the molecule or submolecules we are thinking about are closed in space. It's harder to use message passing when we want to reason about and make molecules or submodules that are far apart to be connected and to share information. So in this molecule here, making these two groups communicate using message passing, it's a bit trickier because they are really far apart. And this brings us to the second problem, which is long-range connections and interactions. We'll start with lifting, which is not weightlifting, but something related to message passing, I promise. And what message passing is, one way of seeing message passing as a lifting procedure is that message passing creates a low-dimensional representation of a node. And what is the information you find in this low-dimensional representation? This low-dimensional representation encodes something about the input space, especially something about the structure that you find around the node. So there is a relationship between what we see in the embeddings and what we see in the input. And if we look at the clusters, as Charlotte was showing last week, if you look at the clusters that we found in the embedding space, we can relate these clusters to specific structures that we find in the input. And then this is the point of view that brings us to lifting. So lifting is a way to, like, we can see message passing as a lifting procedure, as instead of making us reason about just nodes, we can now reason about higher order structures. So we can associate to each one of these clusters a specific structure we see in the input. And through this procedure, we are basically solving the first part of the ill-posed question at the beginning. So message passing allows us to simplify the problem and brings us from the problem of looking at the atoms you have in a molecule, the orbits, and so on, to a space where we can reason about functional groups, molecule, higher order structures. But we still need to find a way to use this information to solve specific problems, like whether a molecule is corrosive or not. And this brings us to long-range jumps, long-range connections, interactions. How to model this? This brings us to something that comes after message passing. So message passing is modeling this interaction between nodes, between pair of nodes or groups of nodes. By doing that, is generating a space where we can where we have clusters representing neighborhoods. From these neighborhoods, once we are in this space, we can use this information to reason in a more structured way about our problem. And one way to do that, in order to do it as a chemist, is apply a form of logical reasoning. So with logical reasoning, we can reason about groups of neighborhoods, find links between them. So we are going from a perspective that is looking at graphs or nodes or graph of atoms to a different sort of graphs that is representing, that we need to come up with, that is representing a graph of higher order structures. In this case, in this example, are functional groups. And to do that, we can do it in 4 steps. The first step is to map each cluster to label each cluster in some way. We can assign an integer, or more easily, as in the last papers you see in the literature, we can assign an encoding. We can do that with a softmax-based activation function or a differentiable clustering approach. But basically, we are uniquely identifying a cluster with an encoding. Once we have this encoding, we can select a subset of the available clusters, of the available functional groups that we are interested in to solve the problem. And we can do that with, for example, attention mechanisms, trying to select only the relevant ones and discard the others. The third step is aggregation. At this point, we have a symbolic representation of these higher-order structures. We have selected the structure we are interested in, and we can combine them and join them to find a higher-order connection between these structures. And one way to do this could be counting the structures we find of a specific type. And once we reach at this level, like this encoding we found is a low-dimensional representation, which is also interpretable in this case, of the higher-order structures we want to reason about. So the last step, it could be to apply a form of structured reasoning to solve the task, like logic or symbolic reasoning. There are mainly 2 approaches. One is really structured and based on the available knowledge. So there are a lot, for example, in chemistry, there is a lot of information you can find in databases that chemists have produced over the years about how functional groups work and so on. So you can compile this knowledge in a program and run a fixed inference to solve, or like a parameter, like you can learn the parameter of this inference, but basically the structure of the inference is fixed. And then you can solve your problem using basically what all the theories that chemists developed over the years. The second form of solving the problem in using reasoning is relax the way you approach the problem in terms of this knowledge. And one approach is to go in the direction of algorithms, so trying to relaxing existing algorithms to solve the problem, or to go completely knowledge-free and take the encoding you have for your higher-order structures and try to solve your problem without any priors. And this, in the end, takes us back to the initial question. So as you can see, like message passing lifted the problem to a way to the kind of terms that a chemist would use to solve the problem, to functional groups. And then with different form of reasoning, we can try to solve this problem in a human interpretable way. And now I will pass to Chaitanya, who is going to talk about deep generative models.